Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing to look at using partial derivatives to evaluate thermodynamic properties. And this time, we're going to be using all of our math skills to look at a question that was on an exam last year. So we have our energy fundamental relations, and I'm going to go through these very quickly, so you'll want to pause the video if you want to study these a little further. We have our definitions of the energy functions. We have the basic set of Maxwell equations. We have some rules for mathematics. And we have a list of measurable quantities. So let's look at this exam question. We have a non-ideal gas heated in a closed system at constant volume from 300 Kelvin and 0.1 megapascals to a final pressure of 0.2 megapascals. And we want to know how much work is performed. So work for a closed system, right? Okay, that's important. For a closed system, work is equal to negative P dV using the chemist sign convention. And then we look at this next part and it says it's at constant volume. So that means volume is not changing, so therefore this integral is 0, and so therefore the specific work is going to be 0 kilojoules per kilomole, or whatever units you want. 0 is still 0. The next question asks about what would be an expression that I could use to find out what was the heat transfer. So we have a choice of 6 different expressions here. Some are in terms of U, some in terms of H. Now, if you go through and look at the first law for a closed system, we end up with this as our general form for a closed system. And we just found that work is 0. And if I further assume that kinetic and potential energy are typically 0, then I have Q is du. And in this case, the change in U is for a change in pressure. And so I have this set of equations for U. I have these for a change in pressure, plus it's at a constant volume path. And so therefore the only appropriate answer is this one. And finally, we have a question about, could we change this to an expression that could be evaluated using specific heat values, R values, and an equation of state relating pressure, volume, and temperature. So we won't go all the way to the measurable quantities. We'll stop once we have derivatives of just these variables. All right, so I'm really just looking at the du dp at constant volume. And whenever I have one of those ugly things, okay, an energy function, something like that, I'm going to use a fundamental relation to get me out of this mess. So du is T ds minus P dV for a closed system. And if I rewrite that as a partial derivative, then it's T ds dP at constant volume minus P dV dP at constant volume. Okay? And then we can simplify that dV with respect to V, or with respect to P at constant V, this is going to be 0. And so we just have this first piece. All right, so what are we going to do with that one? Well, we need to take this and look at it. We have several choices, but with S's, usually the first thing I do is I go and look for a Maxwell. And in this particular case, the Maxwell that relates to this It's really dP ds at constant volume, but that is equal to negative dt dV at constant entropy. So using reciprocals, because I started with the reciprocal, I end up with this. And now then, I have dV dt at constant S. Well, okay, this may not really look like it's better. I have entropy down in the path. And I could use a Maxwell, but that would put me right back where I started. And so my other choice, whenever I'm trying to get rid of something ugly in the path, I have a choice of either going to a Maxwell or going to the triple product rule. So if I use the triple product rule, this is equal to T, so I change the sign, dV ds at constant T, ds dt at constant volume. Okay. Now T ds dt at constant volume is equal to C sub V. But I still have this dV ds at constant temperature. Now again, when I have these ugly things, okay, S is one of my things that I call an ugly thing, I can look at Maxwell's, I can look at triple product rule, I also could do a fundamental relation. In this particular case, I'm going to look for a Maxwell again. I've changed the variable, so I did a different step in there. So if I look this time, ds dV at constant temperature is going to actually have a Maxwell to apply to that, dt dP at constant volume. And at this point, I have derivatives that only involve PV and T. I've got C sub V. C sub V is relatable to C sub P. This is not an ideal gas, so it's not a perfect thing. But at this point, I am completely done with this problem. And at this point, you could take your equation of state, take those derivatives, and complete the problem. So that concludes this video lesson, and thank you very much for your time.